What's up, Raiders? In this video, we're going to talk about how to analyze a series circuit. Now, this is going to be kind of a quick overview. It's going to be based on the assumption that you've already covered previous topics like static electricity, Coulomb's law, resistivity and electricity flowing through conducting surfaces, and law of conservation of energy. So this is going to be quick, and it's kind of assumed that you have that background knowledge. So as always, if you have any questions, you can contact me on the Remind app, but here we go. So in this video, we'll talk about with the series circuit, which means there's only one path for the electricity. We'll use terms and concepts like current, voltage, resistance, the voltage drop, and we'll calculate the power that different devices in a series circuit use. So here we go. We're going to draw a schematic diagram, basically just a symbolic way to represent an electric circuit. So this alternating long and short line, that would represent whatever's generating your electricity. You know, wall outlet, battery, whatever it might be. And so let's assume for this problem that we have the equivalent of a pretty standard United States wall outlet, so about 120 volts. And volts is a measure of electric potential energy. So in this continuous conducting path for electricity to follow, on this schematic diagram, a zigzag line like that means it's some type of device that's connected to your circuit, and it provides resistance to the flow of electricity. And all the wires do as well, but pretty minimal amount. So in this simple series circuit, we're going to set up 3 devices that are connected in your circuit. And the idea is that they're put there on purpose to take that electric potential energy or voltage and convert it to some other form of energy that you want. If it's a light, a radio, a toaster, you're taking that electric potential energy or voltage and converting it to something else that you want. So let's say this first device here provides 15 ohms of resistance to electricity flowing through it. And the second one here provides 5 ohms of resistance to electricity flowing through it. And this final one here provides 10 ohms of resistance. And this is a series circuit because there's only one path for electricity to follow, so it's like a giant single file line. So we'll get to this calculation in a minute, but basically when we're talking about electricity, the movement of free electrons, what we have here is they're going to go from an area of high electric potential to low electric potential. And again, electric potential means voltage. So historically, that was shown going from the positive terminal to the negative terminal. But as years went by, they kind of realized, well, it's really the movement of free electrons, so it's negative charges. So depending on what source you might look at online, you might see some of them showing the older, more traditional way of analyzing a circuit, showing it going from a positive terminal to a negative terminal. But some sources will show going from the negative to the positive. Don't get bogged down by that. The bottom line is, just like water will flow from an area of high gravitational potential energy down to low gravitational potential energy, meaning it flows downhill, electricity, you have the same motion. It goes from high electric potential to low electric potential. So we'll stick with the traditional way of analyzing it, that the electricity is going to go in this direction, the current. But again, it just means it's going from the high electric potential to the low electric potential. It's going to follow this path here. So the first thing we'll take a look at is in the series circuit, in this giant single file line for electricity, you have these 3 different resistors that the charges have to force their way through, and they have 120 volts of electric potential energy to do that. So right off the bat, there's what's referred to as Ohm's law, the basic relationship between how much current or electricity is moving in the circuit, how much voltage or electric potential energy you have, and how much resistance there is to the flow of that electricity. So Ohm's law is this relationship, V equals IR, and a lot of times it's just shown from the perspective of the current, which is I equals V over R. Same relationship, just different variable isolated. So the first thing we're going to do is we're going to figure out the equivalent resistance of this circuit. Because this is a giant single file line, any charges have to move through all 3 devices, so they have a cumulative effect. So the equivalent resistance, it's real easy, just add them up individually. So 15 ohms plus 5 ohms plus 10 ohms means collectively there's 30 ohms of resistance in the circuit. So we could actually redraw this circuit in a simplified format like this. Our electricity source, again assuming a standard wall outlet in the US, 120 volts, will do the equivalent of pushing electricity through equivalently 30 ohms of resistance. So now we can use Ohm's law to figure out how much current is flowing in our circuit. So with Ohm's law, V equals IR, we could rearrange it for current, I equals V over R. Well, for the entire circuit, you have 120 volts of electric potential energy to work with, and it's forcing its way through, in this case, 30 ohms of resistance. So equivalently, you have 4 amps of current flowing. And because this is a series circuit, there's only one single file line for electricity to follow, regardless of where you analyze the circuit, whether you analyze it here as it's going through this first device, if you analyze it here through this device, and so on and so forth, you're always going to have the same 4 amps of current because it's a giant single file line. So we've taken care of the current. Now, we're going to tap into law of conservation of energy. We know from previous work that according to the law of conservation of energy, however much energy your system has to start out, that's how much energy it's going to have later on. And this happens in all sorts of sometimes complicated, hard to follow ways in the body. You eat your food, you get some chemical energy from that. You can convert that to kinetic energy as you move around, things like that. Well, the same thing applies here in the circuit. We have 120 volts, which is really a measure of how much electric potential energy we have. And as the electricity makes its way through these 3 devices, that's the exact amount of energy, that electric potential energy, 120 volts, that's the exact amount it's going to use up. So what you're going to have is you're going to have a voltage drop that represents the amount of electric potential energy or voltage that each device used. So let's take a look at those. So we can say V sub, and I'll label as V sub 15 ohms. That's our way of saying, okay, what's the voltage drop consumed by the 15 ohm device? How much electric potential energy does that 15 ohm device consume? So V equals IR, Ohm's law. Well, we now know that there's 4 amps of current flowing through that 15 ohm device, and that provides specifically 15 ohms of resistance. So that gives us 60 volts of electric potential energy that are consumed just by that very first device. So notice here, if you take a step back, we have 120 volts of electric potential energy to work with. Well, 60 of it, or half of it, was consumed right here. And that should make sense because, again, our equivalent resistance for the whole circuit is 30 ohms. And right off the bat, this very first device, 15 ohms, is half of that 30 ohms. So if the very first device provides half of the resistance in the entire circuit, then it's going to consume half of the electric potential energy or voltage. All right, so now we'll take care of the voltage drops as the electricity goes through the 5 ohm device and the 10 ohm device. So V sub 5 ohm, the voltage drop or the electric potential energy needed or consumed by the 5 ohm device. Again, we'll use Ohm's law. And even though it's a different location in the circuit, in a series circuit where there's only one path for electricity, the current's the same everywhere. So again, it's 4 amps of current going through, in this case, 5 ohms of resistance. So that's going to consume or use 20 volts of electric potential energy. And then finally, the last device, the 10 ohm device, again, applying Ohm's law, different location in the circuit, but it's a giant single file line, so you still have 4 amps of current. Now it's forcing its way through 10 ohms of resistance. That's 40 volts. So collectively, there's been 3 voltage drops, or 3 locations where electric potential energy has been consumed. And again, we did that on purpose. We wanted to convert that electric potential energy to light or heat or sound or whatever we're doing. So if we add up these voltage drops, 60 plus 20 plus 40, that gives us 120 volts. So that's the exact amount of electricity, electric potential energy that we started with. The wall outlet provided 120 volts of electric potential energy. Well, collectively, that's how much was consumed by the circuit. So that's consistent with the law of conservation of energy. Now, let's take a look at the power consumed. Power is measured in watts. And you can calculate it a couple different ways, but one of the ways, and we're just going to take a look at it here, is P equals IV, where you take the amount of current, multiply it by the voltage drop, or how much electric potential energy was consumed by that device, and collectively, that product is the amount of power that that device uses. So, P sub 15 ohms, the power consumed or needed by the 15 ohm device in our circuit. Well, we know that there's 4 amps of current flowing through it, and the voltage drop, it's not the full 120 volts. All 120 volts didn't go just through this one first device, we only had 60 volts of electric potential energy used up here. That was our voltage drop. So 4 times 60, so that's going to be 240 watts of power are consumed by that first device. Then the second device, the power consumed by the 5 ohm device, once again had 4 amps of current flowing through it, but now it only consumed 20 volts of electric potential energy. So that's 80 watts of power consumed by that second device. And then finally, the power consumed by the 10 ohm device, once again has 4 amps of current flowing through it, but it had 40 volts of electric potential energy used at that location. So that's going to take 160 watts of power. So again, I know this was a fast overview, but it was based on the assumption that you had covered a lot of previous material about how electricity moves in general and the idea of the law of conservation of energy. So like always, if you have any questions, contact me on the Remind app. Take it easy, Raiders.